We've now got all of the different types of machines in order, and the different ground conditions that these machines need to work through to build the tunnels that are needed in modern society. So this second part of the program brings us right up to date and gives illustrations of the tunnels that we're actually building now. So we've had the break. The benefits, I think you can see, of mechanized tunneling are evident in many ways. One of the principal benefits is the increase in safety for the workers who have to be underground and excavating tunnels in all different types of geological conditions. Here you can see a tunnel boring machine with drill steel and drilling machines attached that will, in this instance, drill bolt holes for pinning the rock across these fault zones that would otherwise have cause for rock to fall from the profile of the tunnel. Here you can see that the water is literally pouring through those joints. The drilling machines are also used, as you saw in some of the animations, to drive probe holes so that we can get an idea of what is ahead of us, particularly if we're driving in dry conditions and there is the prospect of hitting large reservoirs of underground water. These are other support systems that are used and can be installed behind tunnel boring machines. We've got the wire mesh, which we saw being mechanically erected, held in place with the rock bolt, holding the debris that would otherwise fall. The ring beams, and here shotcreting that is being applied in an open face tunneling method, not with a TBM, but these booms with the nozzle, the shotcreting nozzle, can be mounted on the backup of the machines, as you saw, and if the shotcrete is needed closer to the face, the nozzle can be handheld and shotcrete applied. The canopy, the protective canopy of fingers, you saw the benefit of those, that they provide a protection for the workers that need to be here under very close to the tunnel face, and prior to the bore being fully and permanently lined, if it's to be lined at all. Often in very good rock, the tunnel itself can remain unlined through its design purpose. In many instances, though, depending on the rock condition, it requires a lining of in situ concrete, or pipes are often installed and backfilled around the annulus to create the final product. The shield machines, both for hard rock and soft ground, when they're incorporated, do provide the ultimate in worker protection. here you can see there is no exposure of the workers to the natural ground. You're within the shield at all times. And when the shield is used to erect the precast concrete lining, that is the ultimate in support and lining, in the fact that as the machine moves forward, it is leaving behind it the finished tunnel. In many instances, there's no further need for extra support or extra lining other than the segments that are being built inside the shield. As the machine moves forward, by propelling itself against the lining behind it, you have your finished water tunnel, metro tunnel, road tunnel, whatever it is that you're building at the time with the machine, whether it's hard rock or soft ground. The other major advantage for mechanized tunneling machines and TBMs was the increase in the speed of excavation. Brunel's tunnel was only 400 meters long, but took 18 years to excavate and to build. It wasn't all because of poor geological conditions or the deficiencies and disadvantages of the technique. There were often hold-ups, as I said before, due to lack of funding, and at one point it was delayed for 7 years until they found private funding in those days to keep the excavation going. But today, that 400 meters can easily be achieved in 1 month with modern TBM and tunneling methods. The TBMs are, as you will have gathered, are pretty well purpose-built. They're built for the project to which they are going to be applied. The diameters are often very different from one project to another, even on the same metro system. The diameter of the tunnel machine or the tunnel itself will be different, not so much in the finished internal diameter, but the external diameter can change, giving a difference in the thickness of the tunnel lining, depending on the conditions and the need. Despite that, even if the tunneling machine takes up to 12 months to design, build, and deliver to the job site, assemble, and launch into its drive, by comparison, it will and can finish the same distance of tunnel ahead of drill and blast, which, as you can see, will start and mobilize much quicker with machinery that is pretty much bought off the shelf, but takes quite a long time more to complete. The drill and blast process is several different processes within a cycle to complete each advance of the face, and that imports a lot more time as each process needs to be completed before the whole cycle can begin again. With the tunnel boring machine, as you saw before, it is often the case that you can, with a double shielded machine, you can be excavating the front and building the lining simultaneously. This increases the rate of advance for a tunneling machine and for a tunnel tremendously, which again is an economic way of building tunnels and bringing down the cost. Mechanized tunneling has also allowed a far greater increase in the diameter that can be excavated now with a single full face cutter head. This Robbins TBM cutter head is 14.4 meter diameter and is currently working on a water tunnel at Niagara in Canada for a water diversion for a hydroelectric project. This is an undercutting machine that we heard of before. It was working in Switzerland, in Zurich, for a highway tunnel. You can see the machine is being pulled towards the face. The grippers on this section of the machine inside a smaller diameter pilot tunnel, and the reamer then reaming to the full diameter. The back, you can see the drilling machine, or the drill that is drilling the rock bolting, the drill holes for the rock bolting. Again, a 14.4 meter diameter on the finished tunnel. Soft ground machines too have increased in size tremendously. This one is at 15.4 meters. That's another meter on top of the hard rock machines that we just saw. I don't know how tall is 15.4 meters, but it's, I don't know, 3-4 stories high, a building of that scale. This one here is, 2 of these machines were built and were used in Shanghai recently, just completed the twin bores of a highway tunnel under the Yangtze, with 3 highway lanes across in each tube. These machines have segments in the back, precast concrete segments, building the tunnel as they advance. Another advantage of a mechanized tunneling and TBM tunneling is that the air is clear. The air is clean. There are no fumes. There's no bad after effects of explosives in the environment. Therefore, we can have much longer single headings. Here on the Alp Transit baseline tunnels at the St. Gotthard in Switzerland, these headings from a single access portal from here or coming in from here can be up to, these ones are up to 14 kilometers long, but longer ones have been achieved. On the Channel Tunnel, the longest one was longer than 20 kilometers, 21 kilometers, which was one of the ocean-side pilot tunnels, advanced out from the UK side towards France in a single heading of more than 21 kilometers. It's also helped by improvements, great improvements in the ventilation systems that have been developed to support the tunneling that is being undertaken today. We heard also before that TBMs have been invented and built and designed to excavate tunnels where really in the past they just would not have been possible, not feasible at all. Here you can see both of these are EPB machines, earth pressure balance machines, with the soft material being extruded really up through the screw conveyor and coming out of the discharge gate onto the conveyor to go into the muck skips, pretty much in a homogeneous mud, like toothpaste being extruded. Brunel's tunnel machine or shield would have been working in material similar to that, but he had many inundations that held up the works and took the lives of many of the workers and flooded the works several times. With these machines, everything is controlled in the front. The amount of material taken from the tunnel face is controlled and extrudes. You build just the tunnel that you need as you go forward. Tunnels today now are becoming more and more the social and the environmental preference for many societies that we're living in and developing around the world. This slide shows that if you're looking to increase the capacity of traffic in a city, you have the norm and the need to increase the 4 lanes to 6 or more. Putting them on an elevated structure was the idea in past decades, and many of these structures are now coming down in preference to being underground. And many say that they're being built now the correct way for the 3rd time. They were on the surface, they went up onto elevated structures, and now they're going where they should have been in the first place, underground. And here, this gives a reference to the value of the properties with the different techniques that would be used to increase capacity in the cities. It's not only the value, the resale value of property, it's also the tax value for the property taxes. So if anyone is to say, yes, but the tunnel is a very expensive option, we could build this elevated structure at a quarter or a half of the price. Just say yes, but you'll decrease the value of the property either side and its income value for the property taxes. The ability of modern TBMs to build tunnels where they could never have been before have really created the cities that we know today. And here we can see that in London they are at the moment planning Crossrail to bring heavy rail trains from the west at Paddington Street Station underneath the historic high-rise city centre of London to Liverpool Street and beyond on the east side. Here you can see the Liverpool Street station. It has to connect with all of these existing underground metro lines and bring capacity to have the trains under the centre and the passengers in and out. Here in Seattle, in Washington, they have just recently agreed to a large bore tunnel, double deck, 3 lanes on each deck, for all sizes of traffic, to replace what is at the moment the double deck elevated Alaskan Way highway that was severely damaged in an earthquake in the 80s. And so this is quite an urgent project. And there have been many suggestions that it should be rebuilt, it should be rehabilitated, it should stay as it is, as a double-deck highway at the waterfront. But the possibility of building a tunnel that can do the same thing has won the day. It is going to generate and create for Seattle and all that visit it a much friendlier and attractive waterfront for the citizens and the visitors. So you can see too that the impact, the commercial impact that this revolution in tunneling and tunnel systems has generated across the world. We are one of the few and rare industries that really does go across the globe without borders. You can find tunneling companies, machine manufacturers in every part of the world. These are the hard rock TBM manufacturers that we've heard of. They should all, in fact, be in a row. You can see that they should be all one after the other, and ranging from the 1950s up to date. These ones, the earlier ones. You can see some of the manufacturers have been in the business for quite a long time. Herring Connect just starting recently. And here, the Robbins Company really has started the whole process and the development and invention of the hard rock machines. Some changes, some takeovers. And that's just a few of some of the companies that today are in the business of working specifically with the tunneling industry. There are contractors system suppliers, contractors, machine manufacturers, support systems, Mulhauser, they build the skips that are behind the tunnel boring machines to transport the muck to the disposal sites outside the portals. Roa build the backup systems that go behind the machines, the trailing gear that holds all the support equipment. All of these companies, another contractor, Citroën, they are in the business of the ventilation systems that go behind the machines. VMT, they build the survey equipment that keeps the machines on target and heading in the direction that they're supposed to make successful conjunctions often. So today, we've often asked ourselves, what is the value of tunneling around the world in current dollars? And it's difficult to know, but we're thinking that it's in the region of $370 billion annually. And on occasions, you can really understand that that would be the case when you think that in Shanghai, in the last year alone, and now I've just lost the data, but they are adding between here and in 2010, when they are going to host the expo for 2010, Shanghai is going to add 100 kilometers to their metro system, and that's just the metro system. And that doesn't include the water systems that they're working on, the sewer systems that are needed, the rail and highway tunnels that they're also building. China really is a powerhouse for tunneling at the moment. India is not far behind, also engaged heavily in bringing their cities and their mega cities up to standard with sewer tunnels, water supply tunnels, metros, and road and rail infrastructure across the country. A lot of it requiring long and, in some cases, complex tunnels on the alignments. For all high-speed rail systems that are being proposed across different nations, you can be sure there are tunnels involved, because for high speed, you absolutely need tunnels to take the line straight and with few undulations through the topography. But there's always room for improvement. And here we can see just a couple of the more recent accidents and collapses that have happened in tunneling around the world. 3 of these had nothing to do with the TBM. This was an open face method that was being used to build station cabins at Heathrow Airport in London that collapsed, and you can see everything is falling into it. Here, the shaft failed on the Sao Paulo metro quite recently. Here, the TBMs had come through and had completed the tunnel very successfully in Shanghai. The problem was they used ground freezing in the soft ground to stabilize conditions so that they could create the cross passages for emergency evacuation from the tunnels, the cross passages that link the 2 running tunnels. So they used the ground freezing to freeze the situation and stabilize it, to hand excavate these cross passages. But they allowed the freezing. It's very expensive, ground freezing, so they discontinued the freezing process too early, and the cross passage collapsed, bringing in everything around it. This is the one sinkhole that occurred just recently in Seattle in front of a soft ground TBM. We're not sure what has happened, why this sinkhole appeared, but it certainly is a case of over-excavation. The machine is standing still. The operator is still allowing the ground to be drawn into the machine, and in short time, you'll find that over-excavation is going to create such an event on the surface. So it's a tricky business to control these machines, make sure everything is working safely. A lot of it is in the hands of the operators. The operators need to be very skilled and experienced to make sure that such events don't happen. In all of these cases, well, this one was workmanship, it is believed. This one, I'm not sure, maybe design. And here, technical failure of the ground freezing. So that's also now part of the next part of the talk, where tunneling is going to from here, the improvements that are being, the ability to see further into the face than we can at the moment with mechanical methods, probe drills and things like that. And, oops, I go back to the environmental impact, which Locke, I believe, is going to take over and talk about.
I especially like this part. This is the city of Chicago, and probably all of you have been in Chicago a few times, but very few of you probably know there's 120 miles of 30-foot diameter tunnel under the city of Chicago used for a giant reservoir. Not only the big tunnels of 30-foot diameter, there's a whole series of smaller tunnels. So this network of tunnels sits under the city of Chicago, and it's there just as a big reservoir to collect the water. What happens is they designed, the EPA regulated that you couldn't have raw sewage flowing into the Great Lakes. And so previously what we had is combined sewer and runoff. So when you got more than 2 inches of water, 2 inches of rain an hour, the combined sewer and runoff got together, and instead of going through the sewage plant, it was combined and it was just dumped into the river or dumped into the lake directly, just these outshot pipes you see, and it polluted. And a 40-year event means that once every 40 years it ranges 6 inches an hour, and therefore then you could let that water go out into the unflow, and all the rest of the water you got to store and then put it through your sewage plant. And this they did. They've done it in Milwaukee. The city of Milwaukee's got one of these. The city of Chicago's got one. The city of Toronto's got one. Rochester and Buffalo, Cleveland. They all got these systems, and of course. Chicago being the biggest city's got the biggest system. And so there's 170 or 109 miles of tunnel, all connected into the sewage system, and they pump it in, the water flows down there, and then when the rain stops and things get better up above, they just pump it through it and process it. And it is simply amazing what this has done for these cities, excuse me. The fish have come back to the Great Lakes. Along the lake shore, the property's gone up because you don't have that sewer smell, and it really did transition some of the major cities in the U.S. And it was a boon for the Robbins Company. I think we have a total of 18 machines over there over the years. It helped us develop our technology, and just great for the environment and great for our company. Chicago, fortunately, is a limestone formation under Chicago, and is just all solid limestone, and a nice material to bore, and we've really perfected our machines there. And this is Cleveland. I should have recognized that one right away. Living there. Our plant is right down here someplace. And it again is only about halfway through this whole process of cleaning up the city. You can see some of the, this thing really goes to town too, sorry. You can see that they start out these projects 25 million, 75 million, 210, 260, 150, and now they've got some even bigger ones planned in here because Cleveland had lots of problems with the Cuyahoga River catching on fire and other things, that they're going to put in even some 40-foot diameter tunnel, 45-foot diameter tunnels in Cleveland and collect more water and clean it up further. Yeah, this is kind of, the old tunnels used to use a lot of, instead of concrete to do it, they used ribs and boards, and just putting all this wood underground. And here you can even see it. Even this is done even 10 years ago, but this is all supported by wood. This is steel ribs and boards, physical boards put in to give you temporary support. And afterwards they come in and pour the concrete lining. And yeah, that's what we hope to achieve after, instead of the river catching fire and flames flowing down this little creek here, you get nice clear water and nice vegetation. And that, I can assure you, is happening. And the fish are coming back, and you can catch salmon in Lake Erie now. Not only does it happen in our cities, it happens around the world. We're heavily involved in this project in Hong Kong. And you could, 10 years ago or 15 years ago, you flew into Hong Kong and you got off that plane and you could smell the city. Just the sewage wasn't treated. And we were part of putting, I think we had 9 machines working on this network of tunnels we put in, where they were about 130 meters below the surface. And they're going to expand this further, but it's just tremendously cleaned up the waters around the city. You used to see sewage floating in the harbor in Hong Kong, and all that's disappearing. The Hong Kong project was particularly difficult because of the depth, and the rock was much more cracked than we thought it would be, and so there was pressure, a lot of pressure, problems with the leakage, and different problems. It was a challenge to overcome those difficult conditions. But you can see the size of the sewer plant that they're putting out above these tunnels. And there's a little hard rock machine we built for it. This was built, I think, in Seattle, this one was. And I'd like to say you can see the clear water and the high-rise city now. Now this one's even more interesting, a little closer to home. And this is Boston Outfall Tunnel. The harbor here in Boston is pretty protected. It's back in here, and it became very, very polluted, especially down in Quincy Bay, and all in this area became very heavily polluted. And the government decided and built this tunnel, and the tunnel, 2 tunnels, one from end of Quincy Bay here out into the Deer Island. Deer Island's where the processing plant is, and then from there it is processed and pumped out in the ocean. And about this far out is where the tide starts to, the water starts to flow in, rather than flowing in, it flows out. So they had to take the tunnel out, I think this was 9.4 miles. And in the last mile they put all these diffuser shafts in, so they would process the material, pump it out here, and then dump it into the ocean in the last mile of this tunnel. And in the last mile, they put from the sea, they entered a barge out in the sea and put these shafts in to tap into the tunnel under the ocean floor. And so I think there's 40 of these in the last mile of the tunnel. And this was a case where you all hear, well, what do you do with these machines when they're finished? In this case, they actually did drive this tunnel machine out and left it right here. The machine was just left. And the tunnel was lined as it was bored. But again, it cleaned up all the water in the bay. This whole area was all polluted, and you could just see all this pollution in the bay. And now when you go out there, fly over this thing, it's a whole different environment, and cleaned up this total bay. Whoa, got carried away, sorry. Okay. Yeah, this is this yours, Joe? You're not yet? I'm still going, am I? Okay, sorry. Yeah, there's lots of problems around the world where the rivers are polluted. It's still a way too much and a lot of work to do. This scene here is all too common still in India. We haven't solved that complete problem, and this is the Yangtze River, and this is Shanghai, modern Shanghai behind you, and still have this pollution down here. So there's a lot left to clean up in the world. There's this beautiful tunnel I like very much that we're starting to bore on in India. This is for irrigation, and this tunnel is going to be one of the longest tunnels we've done. There's a 43-mile, this is a big national tiger park, and there's 43 miles of tunnel to be done on this, and so we've got one machine started on this end, another machine started on this end, and it won't daylight through the whole 43 kilometers, and it's for irrigation. When the monsoons come, the water rushes in, fills these big reservoirs, and then when it's through the rest of the year, they're just going to pump the reservoir and irrigate all this poor farmland down here, and it's really a nice project. It's just a good feeling to go down to these projects and have these tunnels be put in and think that they're going to benefit all these poor people out there working on the farms. It's just a nice thing to see. And that's the machine set up down in the tunnel, ready to go. The bore 22 miles of tunnel. You can see all the infrastructure that's required just to develop the tunnels. You need concrete plants and facilities and ventilation and muck cars and conveyor belts and just a whole network of process just to put these tunnels in. I think now you're on renewable energy.
And just continuing on with a few more about the projects we've done in the sections on renewable and our energy, in our case largely hydroelectric projects. This is the Svartisen hydroelectric project that took place in the late 80s in the northern part of Norway, just above the Arctic Circle. 57 miles of tunnel were driven by, I believe it was 5 tunnel boring machines from Ravens. Svartisen is black ice. There's a big glacier here, and these various tunnels collected water from the runoff, the melt from this glacier, and directed it into a couple of different, one large hydroelectric plant over here in the Kilvik area. They're saying that Norway's now producing 28% of its energy with hydropower. That was 5 machines, and these were the first machines to use these 19-inch cutters, which are intended for the hardest rock. And this is a typical kind of photograph in front of the machines in this very good, boring, confident rock with someone out front inspecting cutters. Today, the vast majority of the machines have cutter heads which allow replacement of the cutters from the backside. This is another hydroelectric project that was completed just recently, Kárahnjúkar in northeastern Iceland. And this project was built in order to provide power for a new Alcoa aluminum smelter, 4,600 gigawatt hour per year plant. There were 3 tunnel boring machines used to bore 25 miles of tunnel, 1 machine boring from this section meeting here, another machine boring out this direction, and the 3rd machine was introduced here, bored this direction, then was retrieved in reverse direction, bored in order to meet the 2nd machine coming in here, and finally at completion another one of the 3 machines continued on this tunnel. And very difficult geology, running from very hard rock to very mixed ground, and at times water flows up to a cubic meter per second into the tunnel. There was a lot of probing, grouting, and so forth required. It's a pretty extreme environment, as you can see by this photograph. Very remote location and pretty darn cold. And it was a challenge just to get all the machines assembled and started under these conditions. it was quite an interesting project and carried out by an Italian contractor. But visiting the canteen at this site was like going to the United Nations, as they had workers from about every European and Asian and South American country you can imagine were in the canteen, and you could get food of just about any type you wanted. It was really an incredible project. One of the machines on this project set a world record, boring over 100 meters in 24 hours, which was quite amazing in the sort of geology we were working in, and for a machine at 8 meters diameter. This is a project that is just starting today in China. There will in fact be several hydroelectric projects that are installed along this Yalong River. We commonly refer to these as run-of-river projects, wherein we're taking advantage of an elevation drop in a river, usually involving some sort of bend like this, where we can bore a tunnel across and take advantage of that potential energy. This project involves the use of, or will involve the construction of 4 tunnels that are each around 15 kilometers, 16 kilometers long. 2 of these tunnels will be excavated by a tunnel boring machine, and 2 of them by drill and blast methods. They're 12.2 meters diameter. This is the Robbins machine going together on site. Again, you can see it's a pretty remote mountainous region. The machines also will pass under high cover at nearly 2 kilometers of rock above the tunnel, so it's going to be very challenging to support this rock and deal with elevated temperatures probably. The machines being this large, it's difficult to find both factories large enough to assemble them prior to going to the site. It also takes a substantial amount of time. Most tunnel boring machines are completely factory assembled and tested in the factory before they're delivered to the site. This and the Niagara and some other recent projects we've done have been the first machines which were completely fabricated and never completely assembled in a factory. These machines, all the pieces met up for the first time ever at the job site and put together, which just requires a lot of quality control in each of the steps of manufacturing, and of course project management and logistics control to get everything there when it's needed. The next section is a bit on some irrigation projects that we've been involved in. This is the Lesotho Highlands project, where water was brought from the Lesotho Highlands to be used in Johannesburg region. It was done in the late, early to late 90s. 45 kilometers of transfer tunnel and 37 kilometers of delivery tunnel to take all this water, and as well as some new dams for transfers. Several tunnel boring machines were involved. Here's a picture of one of the completed dams. This is a photograph inside of one of the tunnels as it was being constructed, and again a photograph of the machine as it's assembled outside, ready to start on the south delivery tunnel. The north delivery tunnel, 10 miles long. And all of the tunneling was completed in 1994, and here's a typical photograph of breakthrough on target at the completion of the tunnel. This was a project again back in China, the Shanxi Yellow River Diversion project, where we did over 50 miles of tunnel using 4 double shield tunnel boring machines. This is a case, as Shani was pointing out earlier, of machines which bored and erected lining as they proceeded and had completed tunnels when the TBMs were done. This is a photograph of one of the machines going together. This project had extremely good advance rates. Here's record of the 3 machines on the first part on, I think this was lot 2 and 3 of the contracts. These are advance rates by month for all 3 machines, and as you can see, the average of these machines was around 800 meters per month per machine for the duration of this 50 miles plus of project, and that's completed tunnel because they were lining as they advanced. One of the machines, in fact, on the next section of the contract, bored 13.5 kilometers of tunnel in 10 months, averaging over 1,000 meters a month of completed tunnel. This project is taking place today in Peru. It's a Trans-Andean tunnel bringing water from the eastern side of the mountains and the very wet jungle side of the Andes to the arid west of Peru, where it will irrigate 130,000 acres of farmland. It will, in its second phase, also generate electricity. This is also a challenging tunnel in that it again has high cover of around 2 kilometers of cover and expected to have very high heat in the tunnel as we construct it. 5.3 meter diameter machine, started boring in 2006. The tunnel now is about 80% complete. The machine has also 4 chiller units on it in order to keep the tunnel working temperature down to an acceptable level. And I've been in that tunnel lately and it's quite warm. This is back to the Alp Transit Tunnels that Shinny was talking about earlier, very long tunnels. This is the Shanxi basis tunnel, where you just had a machine doing access tunnel to this main line, and the main line, I assume, is going to be contracted soon. There were machines already boring on this section, Bodio to Fido, and now continuing Fido out, and another section from Amsteg. And will end up resulting in high-speed rail tunnels that will, of course, be fitted to carry truck traffic as well, meaning that all the traffic that today is winding its way up through the Alps, through these small villages and down the other side and causing a great deal of pollution and traffic congestion will all be eliminated, and of course move much more freight much more efficiently through the Alpine region. 5 TBM so far on these sections, and this is only the beginning of these Alpine tunnels, as more and more of them are coming out today in Italy and in Austria, as well as they begin to build their Transalpine rail systems. This is a very interesting project in Kuala Lumpur, a multi-use tunnel. It was a large diameter. I don't recall the diameter. 13 meter diameter. The tunnel is intended to provide a traffic tunnel, as well as in the bottom is a typical stormwater runoff, but during monsoon seasons they were actually getting inundated and causing massive flooding, and the tunnel can be used, in fact, to deal with floodwater runoff and divert an enormous amount of water to prevent flooding in sections of the city that had occurred forever prior to that. There were 2 machines used to bore these tunnels. They're not all that long at 3 miles plus, but the project is now completed and in operation as of mid-2007. Sub-aqueous hard rock tunneling. This was a fairly interesting project under the Elbe River in Germany. Again, a fairly short 1.5 mile tunnel. Very complicated geology, working under high water pressure, and no ability to evacuate the face, as I mentioned earlier, so there was no way to actually get in front of the machine to do maintenance. So each of these cutters is actually mounted in a way that allowed a man to enter the backside under atmospheric conditions, and the cutters could be removed under sealed conditions and brought into atmospheric while the face, was still under high water pressure. It was take a lot of time to change and maintain cutters, but it was possible to do so, and it was probably the only way to do that particular project, as it was deemed impossible to use freezing ground methods in this geology. And I think at this stage, if we go back to Dick, who will wrap up things for us. Thanks for your attention today.